Hello and welcome back to FTC Getting Started. My name is Gordon Dotterman. I'm from FTC Team 8372 Trial and Terror, and today we'll be going over the basics of autonomous movement and the making of methods.
So the first example we'll be looking at today is a time example, and this will be using simply sleep method to be moving forward for 1 second, stopping 1 second, and turning left for 1 second, and then stopping. Now, the sleep function does, if you don't know, is it just completely stops the thread that your program is running in, and so this is pretty much just a wait. This is a wait 1 second. You can't do anything to motors while it's waiting. You can't do any adjustment. You can't look at sensors. It's just going to be stopped right here, right here until those 1,000 milliseconds are over. And this can work pretty well for just roughing out distances. However, a few issues with time-based movement is that one, it can depend on your battery. So the stronger your battery, the further you'll go, and time won't be able to change that. And then the other issue is that with sleep, as I said before, you can't pay attention to anything. So if something happens or a sensor realizes that you're already there, you can't do anything. You just have to keep moving until that sleep is over. So now we've gone over the pros and cons, we'll make a quick method for this. So we'll make it down here and we'll call it void move. And what it'll take is it'll take a double speed, it'll take an int time ms, and I include the ms so that whoever's using this function, whether it be you or somebody in the future, knows what unit of time it's taking. So what we can do is we can say left drive dot set power to speed, and then right drive dot set power to speed, and then say sleep for time ms. So we'll just add this in here. We'll say move. We'll take the speed as 1 and 1,000 milliseconds, just as before. And we'll say here, we'll say move 0 for also 1,000 milliseconds. Now, one thing you'll notice that's lacking in this function, or this method, is that you can't really turn because the speeds will be the same. You can make two variables, so double speed L and double speed R, and simply set them to those individually. Now you'll notice that our previous methods don't really work here because there's now two speeds instead of one. And what we can do here is we can override our function by simply having a void move, which instead takes a double speed and an int time ms. Now what we can do, instead of having to write all that again, is we can simply say move speed time ms. And so this way we don't have to change those. And here we can say move 1, -1, 1,000. So the next method we'll be looking at is one which utilizes the motor's built-in set target position. So because of motor encoders, motors have those plugged in are able to take in a target position of encoders and move towards those at a variable speed until they get there. And then the method is busy basically tells the user if the motors have gotten to that position yet or not. So if it is not, it will return true because it is still getting there, and if it has gotten there, it will return false. So what we do here is we simply set the target position to 1,000 and 1,000. So both of the motors will go forward 1,000 encoder points. And then while both of the motors are busy, you keep setting the target position. And then what we have down here is we set the left drive to target position of 2,000 and the right drive to a target position of 0. Now the reason it's 2,000 and 0 is because the encoders aren't able to reset. So when you want to turn, after moving 1,000 encoders forward on both motors, you rather want to move forward 1,000 on your left drive and backwards 1,000 on your right drive, which adds up to 2,000 and 0 respectively. So the issues with this is you can't really change the speed. The motor class figures out the speed on its own, and so there is no editing of the speed while it's moving to a target position. It'll just figure out what it needs to do. which can be both good and bad depending on the situation. So what we'll be doing for the method here is we'll make a void move method, and because we can't change the speed, we'll simply take two distances. So int distance r and int distance l. And then we can just copy paste in here, distance l, distance r. So once we're done with that, we'll notice that a key issue. So here we can change this, so we can just say move 1,000, 1,000. And for this one, we can say move 2,000 and 0. The issue comes when you want to move multiple times and at strange distances. So let's say you wanted to move 500 after this and then turn for 300. It gets complicated to try and keep track of those encoder values as you move along, because you're constantly having to do the mental math of, okay, if I want to move forward 500, what are these two distances going to have to be? So what you can do in your method is you can change your distances based off of your current encoder positions. So you can say distance r equals distance r plus right drive dot get current position. And then for the same for distance L. Now what this does is, let's say here, instead of having to say 2,000 and 0, we can instead say negative 1,000, which is what we really want, and then 1,000. And that'll add on to the already 1,000 and 1,000 encoder values we should have after this movement function. This also protects against issues such as drifting. Let's say you do something in between these two functions. Something might happen where you don't entirely know how far your robot has gone, so those encoder values that you've calculated of like 2,000 and 0 wouldn't work. So our next example here is a more complicated yet much easier to work with version of encoder point movement. So what we have here is, instead of using the set target position, we simply use just get current position. So what this allows us to do is it allows us to change the speed. So as you can see here, we set our own power. So we have getting our left position and we have getting our right position. And you can see we're implementing something similar to what we did with our method last time, which is finding the difference between our initial movement and where we want to be going. So while the difference between our current position and our starting position is less than 1,000 for both of these, then we're setting the power to 1. And then for the turning, what we have to do is, instead of this less than 1,000, is we actually have to say greater than negative 1,000, because it'll start at 0 and count down as the power is set to negative 1. So this allows you to change the speed, set it to your own variables, do curves possibly if you can figure out the encoder values for that. It just allows you to be a lot more versatile, both in your direction and in the sensors you use. So the method that we're going to make for this, we'll call it void move once again, will actually take a speed this time, and it'll take a single distance. And we can override this if we want to. But all we'll do is we will have all of this in here, and instead of less than 1,000, we'll do our distance, and then instead of 0.75, we can do speed. Now, one issue with this is, let's say you want to move backwards. This number will be going negative, yet this number, because it's already started as negative, will be less than this, and therefore it won't move at all. So what we can do to combat this is use the built-in function math.abs. And what this allows, so you math that absolute value of these two, and then when you use this function, you only input positive distances, even if you're moving backwards. And then this allows you to get the distance you have gone from where you started rather than the signed distance. And this will make this work for negative movements as well. Now another issue with this is turning, and that can be fixed by a multitude of things. However, at this point, because there are so many variables being set, oftentimes I find it most useful to create a separate function. Now you can either do this or you can do a double speed L, just like we did in a previous one. So you can do a double speed L and a double speed R, and this will work. However, I personally like it, if I'm doing a turn, is to rather have a turn and just have a single speed, and then instead of this, you just negate one of the speeds. What we can do up here, so we can say move speed of 1 and 1,000. If we want to, we can also just get rid of this. You could also overload it if you want to, but because we already have a turn function, there's no need for that. Then what we can do here is we can say turn at a speed of 1 for 1,000 as well. So one of the last things we'll be going over here is how to use a gyro to turn. So what we've got here is while our target heading, so in this case 90, is not equal to the current heading of our gyro, we set the power to the difference between our gyro heading and our target heading divided by 45. Now this may seem a little confusing. However, what this is really doing is it's finding the difference between where you want to be and where you are, which will get smaller as you're closer, and then dividing it into a number that your motors can use. Now, different people use different numbers. I personally use 45. However, this can vary from person to person. Some people use 30, some people use way smaller numbers. So what this will do is if the robot is really far away from the target heading, so let's say we start with 170 and 170, then the robot will be turning very fast, and as it approaches its destination, it will slow down. So for our method for this, it's pretty straightforward. It's not going to be trying to be both a turn and a move at the same time. Instead, we're just going to have is turn to, and all we need is a int target heading. Now what we're going to do at the beginning is we're going to do gyro.reset the axis integrator. This will reset the target, the current heading to 0 that we get from gyro.getHeading. And then what we will do is we will pretty much copy and paste what we have here. So we'll take target heading and target heading. And we can replace all this with turn to, and then we can just say 90, as we said previously. Now, the nice thing about this, that a lot of people don't notice, is that you can also turn in the opposite direction if you just put in a negative number, because then the difference between these two will be negated, and therefore these two will be negated, effectively switching which way you're turning. So one issue that gets overlooked a lot, even especially by me, is not noticing the possible issues in your power variable. Now, motors can only take values from -1 to 1. So to get 1, our max value, there would only have to be a difference of 45 degrees between gyro.getHeading and our target heading. If it's anywhere past that, we'll get something above 1, which will crash our program. So what we need to do to combat this is use a range clip. So what we can do is we can say range.clip, and then put in parentheses here. I'll import that real quick. And then we've got range clip our power, and then we need a minute. So we have our number, and then we have our minimum, which will be -1, and our maximum, which is 1. And then we should do the same thing for this, except with negative power. Now, some people use different minimums. I personally use 0.8 for my minimums and my maximums on turns, because if the robot starts turning too fast, it can sometimes speed past where you actually want to get to. just because the sensor isn't able to update in time to tell the robot. So our final example here is just pure adaptability on movement. So while a lot of teams do use gyros, I see fewer use them to move straight in their programs, which is a very crucial part, especially depending on your drivetrain. If your drivetrain is holonomic, or it basically isn't tank treads, you can have issues with moving straight. So what this does is it resets our z-axis integrator, like we do in our turn, and it gets our initial positions, just like in our previous encoder positions method. We set, we're in our while loop, and then we have this variable called correction. And what this does is it simply gets our gyro heading and divides it by 45. And then it adds that to our speed, which in this case is 0.75. So what this will do is, because gyro.getHeading should be 0 if it's moving perfectly straight, as dictated by resetting our z-axis integrator here, any difference in that should be corrected. And so by subtracting from our left drive and adding to our right drive, if the gyro heading is positive like 3, that'll be a small positive number. It will take away from the left drive and add power to the right drive, therefore correcting what is currently off. So for this method, it's pretty much a combination of all the previous ones we've done. So void move, and then we have our speed. We have our int distance, and really all we have to do is put this in here with, instead of 0.75, put in our speed, and then instead of 1,000 we can simply use our distance. Once again, you'll notice that this can be if you're trying to move backwards, this can be an issue. However, once again, you can simply do math.abs of both of the left side specifically, and then you'll be able to move forwards and backwards as long as you put in a positive distance always. And there you go. That's how you would move forward in a straight line in Android Studio. I hope you found this video useful, and I hope to see you out on the field.